Hello and welcome to my presentation about our latest work, instant segmentation and fitting of excavations in subsurface utility engineering. Let's start with the question why we should even care about underground utilities. Well, because inaccurate information about certain utilities can be a big risk and may lead to costly damages, reaching billions of dollars each year. The big challenge is poor and limited records of underground infrastructure. Documentation standards are non-existent, and in most countries there is no obligation to report new installations. Right now, the most common method for documentation is on-site surveying and manually altering of data. How can we improve this workflow? We've developed a solution that not only makes documentation easier but also allows for an interactive on-site data exploration. Construction workers create georeferenced 3D reconstructions of excavations using mobile hardware. Pipe-like structures are then segmented in the reconstructions and further used to align misplaced data. In our paper, we present four main contributions to enhance subsurface utility engineering. We describe a suitable segmentation approach to detect pipe-like structures in noisy 3D point clouds captured from the ground level. Further, we show an efficient alignment approach of the segmentation output. We also show the real-time feasibility of this algorithm in an AR application. Accuracy of our approach is tested on synthetic and real excavation data. Let me walk you through our algorithm. To handle noisy 3D data effectively, we apply a multi-view segmentation approach on image renderings. We determine the centers of pipes in image spaces and then map these back into 3D space by creation of planes from the camera centers through the segmented images. Intersection of those planes yield the actual center of pipes in the 3D data. The segmentation results are then used in a least squares optimization for alignment of the given pipe data. At the beginning, the user specifies the pipe colors, a starting point on the pipe, and the distance of the renderings. For initialization, we will start with a bird's eye view rendering of the pipe from the given starting point. During the rendering process, we make use of far and near clipping to remove fore and background noise. Next, we perform simple color-based segmentation in HSV color space to create a mask of the pipe. To determine the direction of the pipe, we apply a minimal fitting rectangle on the mask. The angle of this rectangle corresponds to the heading direction of the pipe. With the known direction, we can align the walk direction along the pipe. This allows for rendering images around the pipe. Again, the images are rendered with fore and background. Further standard preprocessing like Gaussian noise is applied too. Then the mask of the pipe is created via color segmentation. Distance transform filtering is used to estimate centers of the pipe. Further, a vertical filter is applied to enhance the desired center. And in the end, a line fitting approach is used to get the final center estimate in image space. Now, we want to reproject these results from image space into 3D. Therefore, we span a plane from the camera position through the image space segmentation. This is done from multiple views around the pipe. Again, also here results are reprojected by spanning a plane through the image space. These planes are now intersected to obtain the actual pipe center in the 3D reconstruction. Intersections are given by a 3D point in between the camera positions and the direction vector, which should correspond to the pipe heading direction at the current step. The reset point of the segmentation step is saved for the alignment process later on. Then the new candidate points are calculated and the segmentation step is repeated at the new candidate points until there are no valid segmentation results found. The alignment is done via a simple least squares optimization problem. 3D points obtained during the segmentation are fitted to GIS polylane data, which are consecutive line segments representing the pipes. Therefore, the minimization problem is to align these line segments to 3D points, which is quite simple and fast compared to fitting complex 3D data structures like point clouds or meshes. This video shows the algorithm running in a live AR application. Since the whole segmentation and alignment process only takes a few seconds on an iPad, it is suitable for on-site operation scenarios, as you can see here. We evaluated the segmentation on a dataset of 30 real-world excavation reconstructions. The fitting approach was further evaluated on synthetic data. The evaluation shows an accuracy of less than 10 centimeters for the proposed segmentation approach, which is within SUE constraints of about 20 centimeters. Rotation errors remain mostly smaller than 1 degree, but contains inconsistencies in a few cases. Like poor rotation estimations can occur due to bad segmentations at pipe ends. However, our results are clearly usable for the translational alignment, which is the typical error in such data. Experiments using Seagull on the given dataset showed it did not work very well on the noisy data, while also being too slow for real-time approaches used on site. To wrap up, we can successfully link real-world pipes and given documentation data. This enables enhancing on-site work by using a digital twin, updating GIS documentation right from the field, or also for offline usage with tools like QGIS. Further work is solving estimation issues at the edges of excavations and using our algorithm to build a ground truth database, which could help enable deep learning applications in the future. Thanks to the whole team, and feel free to contact us if you have any further questions. Thank you.